As indicated on the sheet here on this page, we're going to be discussing rational functions from section 11.5, but we're kind of picking up in the middle of the discussion. If you have the exploration sheet for section 11.5, we're going to be starting with the second part of that, the second sheet, and it's with number 2. The entire first sheet is what contained number 1. We'll do a quick review of some of the main points from that before we get started with number 2. Number 1 was dealing with this function f of x right here, looking at what happens when x gets really close to -2 and +3. As we can see, plugging -2 into this function would actually produce 0 in the denominator, and so would plugging in +3. The thing is, you don't have the same thing happen for each of these situations. Plugging +3 into f, as you can see, gives us 5 over 0. When we look at what's happening as we plug in numbers really close to 3 for x, we can see that, like for 2.999, something really close to 3 on the lower end, we get 5 over a small negative number, right? Because 2.999 minus 3 would give us some very tiny negative number in the denominator. And when we plug in something like 3.0001, we would get 5 over a small positive number. Now, 5 divided by a small negative number, that is a very large negative number. Essentially, we're heading towards negative infinity with those numbers, the closer we get to 3 from the left-hand side. And from the right-hand side, the closer we get to 3, we're heading towards positive infinity. So what ends up happening with the graph for this situation close to 3, go with 3, is we saw that let's see, from the left-hand side we're heading towards negative infinity, so we saw this kind of thing happening from the left and right, and we end up with a vertical asymptote at x equal to 3. All right, so this situation where we have some number over 0, we get a vertical asymptote. So what's going to happen now when we plug in -2, as we see? Well, we get something a little different, actually. We end up with 0 over 0 in this situation. And if we take a look at some numbers close to -2, it's not quite as clear what's going to happen with the fraction here. As we can see, plugging in a number just to the left of -2, we're just going to have a small negative over a small negative, and plugging a number just to the right of -2, we have small positive over small positive. So it's really, we can't conclusively say, well, it's heading towards negative infinity or positive infinity. In fact, we don't really know what number it's going to until we do some simplifying of our fraction. So this is kind of a strange case. It is undefined in a sense because we can't divide by 0, but it's not determined, just like it is over here where we have the vertical asymptote. Of course, you've probably been saying, Mr. Whipple, why don't you just simplify this function and get it to here? And that is indeed what we do. Okay, these two functions right here with the x plus 2 over it and then the simplified version are essentially the same function. However, there is one caveat. We cannot plug in -2. So this is not exactly correct until we put such that x cannot equal -2. I meant to say -2 earlier if I said 2. All right, so now they're the same function. So what's going to happen when we try to graph this function, right? What we see is it's going to look exactly like the graph of 1 over x minus 3, okay, which is just the basic hyperbola here. However, When we get to -2, somewhere along the line here, when we get to -2, it's actually just going to be a hole. All right, that's what we found. And then it's going to go on and do that. So this situation where we have a hole in the graph is what we call removable discontinuity. All right, that's what results usually when you have 0 over 0. Removable discontinuity. Try to spell that right. So that's our review of what was on page 1, or the first sheet of the exploration. Now let's head to the second sheet, starting with number 2. I'd like you to use what you just learned on the first sheet of this exploration to go ahead and do number 2 here. See if you can answer these 3 questions. Just to give you a little hint, it might be helpful if you factor the numerator up on the top. So why don't you pause the video, give this problem a try, and then you can check your work with what I've done. See if this is what you got. So now we're going to go through a number of examples where we're going to be graphing rational functions. And in order to do that, we need to find information. First of all, as you can see in part A, we're going to find out about any discontinuities, which really means anywhere where we have vertical asymptotes or removable discontinuity. All right. Then part B, we need to figure out what's the long-run behavior of the function and see if we have any horizontal asymptotes. All right. And then part C, we're going to be doing some things we're pretty used to, finding x-intercepts. Part D, we're just going to find the y-intercept. And once we have all of that information, we should be able to sketch a pretty good graph of each rational function. All right, so let's get started with this first one, and we'll do this one together, and then you can practice on others. So the very first thing I'm going to do here is to see if I can factor the denominator, and I believe that is a difference of squares, so we can factor it into x minus 1 times x plus 1, and immediately we can see that there are 2 factors that are identical. So this function can be simplified to 1 over x minus 1. However, we do have an issue with x being -1. That would produce the 0 over 0 or an undefined situation. So we do have to keep in mind that x cannot equal -1. But which kind of discontinuity is that? Remember, if you can cancel out the factors, that means it's the removable discontinuity, right? This is the one that's going to be the whole. And then we also have a situation in the denominator where we'll have 0 if x equals 1. Right, so if we're looking for discontinuities, that's where we kind of set the denominator equal to 0 and solve for x that way. All right, so we have removable discontinuity at x equal to -1, and then we have a vertical asymptote of x equal to 1. So I'm going to go ahead and put that vertical asymptote in here. Here's x equal to 1, and then as far as the removable discontinuity is concerned, we're just going to have to remember to do that when we get to the end of the problem. However, we're going to use to do this problem. Let's just use a simplified version of this formula now. Okay, so moving on to the long-run behavior of this function. Let's see, so LRB we know is going to be the highest degree term from the top, which looks like it would be x, and over the highest degree term from the bottom, which looks like it would be x squared. So that will simplify to just 1 over x, and this is that situation where, you remember, we're thinking as x approaches plus or minus infinity, what's going to happen to the 1 over x, or the y. So y is basically going to be heading to 0 because our denominator is getting so big. So that would tell us that we do have a horizontal asymptote, right, of y equal to 0. So let's just kind of mark that here right along our, didn't mean to change colors there. So right along our x-axis, y equal to 0 is a horizontal asymptote. All right, now let's check out the x-intercepts. We know with x-intercepts, right, that's when your y value is 0. So if we just set the function equal to 0, we'll have x plus 1 over, I'm sorry, I don't want to use that function. I want to use the simplified version. So we'll have 1 over x minus 1 equal to 0. And essentially, guys, when we do this, of course, we're going to multiply over by our denominator. So we'll just have 0 times x minus 1 equals 1, which gives us 0 equals 1. So anytime you do this, you're just going to multiply the denominator out of it, this denominator out of it, and you're going to just be setting your numerator equal to 0. That's when your fraction equals 0, is when your numerator equals 0. Well, in this case, our numerator can't equal 0 because numerator is just equal to 1. So therefore, we have no x-intercepts on this function. All right, so we don't need to mark any of that. And then finally, let's finish off with the y-intercept. Of course, that means we need to let x be 0. So x equal to 0, so we'll have f of 0, equaling, in this case it'll be 1 over negative 1, so that equals negative 1. Alright, so we'll mark that point right here. So at this point we have lots of information that we can draw upon. Alright, as we go over to our graph, we can kind of start to see what the graph has to do. It has to go through this point, but it also has to conform to this horizontal asymptote as well as this vertical asymptote. So you can already see, what the curve's going to look like. It's going to come down and do that. It can't cross the x-axis because we don't have any x-intercepts. So here we go. Let's sketch it in here. Maybe start a little closer there. We'll come down, and it's just going to go down and conform to that asymptote there. All right. And now we just need to take a quick look over at the other side. Over here we also have values, and we're either, there's really a choice. There's two things that can happen. It can conform to this asymptote and then the horizontal like so, or it can do the same thing down here below. So let's just plug in, a value like x equal to 2 and see what happens. So if we plug 2 in over here, we'll have 1 over 2 minus 1. That's positive 1, so we know we must be on the top side, and we can come over and just sketch our graph real quickly, coming down. There we go. Alright, so that's our graph. Let's go to the next slide, and you can get some more practice with this. I don't think there's any tricks to this one. It's pretty straightforward, so why don't you do the analysis up here in the boxes, or in the boxes that are provided on your paper, and then see if you can sketch the graph. Alright, you can pause the video and give that a try, and then see if you get the same thing I get. Alright, see if this was what you got in the boxes. Alright, so here is the information we have. I found a vertical asymptote at x equal to 2, horizontal asymptote at y equal to 3. We've got an x-intercept of negative 2/3. As you can see, we just end up setting our numerator equal to 0, and then our y-intercept is negative 1. So I've marked all that over here, and I think we can see pretty clearly what's going to happen on the left, and then you might need to just try a number to see whether you're up in this space here or down in this space. Though there is a way we might already know, but go ahead and sketch your graph and then see if it matches what I have. Check and see if this is what yours looks like. Okay, not a lot of guesswork over on this side of the graph as to what's going on. Up here you might have plugged in, say, x equal to 3, but if you do, you're going to get a sufficiently high number. I think you get, 11 over 1, so we know it's got to be up here. Also, we kind of know because if it was down here, then we would have an x-intercept over here, and we know we don't have one, so that's another reason to kind of figure it's going to be up in that space. Alright, let's go on to the next one. like with the last problem, I think we can see here there's not going to be any removable discontinuity. We definitely have some action going on in the denominator, and when we set the denominator equals 0, I think it's pretty easy to see, or pretty clear to see, that we're going to have what x. We're going to actually have two vertical asymptotes, right? Our vertical asymptotes are going to be at x equal to 1 as well as x equal to 3. All right. Now don't let that throw you too much. Okay, if we go ahead and draw those in, all right, x equal to 1 and x equal to 3 right here, it just means you're going to have to make sure that you're checking on all sides of your asymptotes. All right, so when you graph, you're going to have one part of the graph being over here, and then one part in the middle, and then another part over on the right hand side. So don't forget to make sure you're doing parts of the graph on all sides of your vertical asymptotes. All right, that's all I'll say for now. Pause the video and see if you can do the rest on your own. All right, check and see if this is what you got. All right, so let's see. We already talked about the vertical asymptotes and drew those in. Long run behavior, our y is going to tend towards just 4 over x squared, right? Highest degree term, top and bottom. And that means, of course, as like we saw in one of the examples before, as x approaches plus or minus infinity, our denominator is getting huge, which means our y is heading to 0. So that means we have a horizontal asymptote of y equals 0. For the x-intercepts, set it equal to 0, and we saw this before as well, which tends to happen sometimes when you have a horizontal asymptote that's also at 0. But we have no x-intercepts, and I should actually, let me correct this. It's not that 0 equals 4. 0 does not equal 4, so no x-intercepts. All right, and then we plug in 0, and we got a y-intercept of 4/3. So pretty obviously we can see what's happening over here. But were you able to figure out what's going on in the middle? All right, in the middle, what I would do is just plug in -2. See what not -2. Plug in +2 in your function, and let's see, if we plug in +2 up here, we're going to have 4 over 1 times -1. So we'll end up with -4. All right, so that tells me that we're down in this space, and we have to go through this point at what, 2, -4, and conform to our two asymptotes here. So pretty much the graph's going to have to do something like this, kind of like we saw with secant or cosecant graphs. Conform to our asymptotes there. All right. And then let's also check to the right of x equal to 3. And if we were to plug 3 up into, let's plug in 4 up into our function here. We'll have 4 over 4 minus 1, which is 3, times 4 minus 3, which is 1. So let's see, it looks like we'll have 4/3 right there, okay, which tells us we're up here on the positive side, and so our graph must do this. We'll just bring it on down. That was not very well drawn. Let me take that back and try again. So just come down and conform to our two asymptotes there. All right. So let's go on to the next one. These last two problems get a little interesting. I'll say for this one, there's really not too much trouble with the discontinuity. You can see I've already factored the top, and we can see there's no removable discontinuity. I do think we'll probably have a vertical asymptote. Where you're going to find things to be interesting is when you check the long run behavior. Okay, you can see we have a square on top and the x on the bottom. So there may not be any horizontal asymptotes, but there might be still an asymptote. All right, so why don't you go do your analysis and see what you come up with, and then you can check. So pause the video right now. Okay, see if this is the information you got. Okay, so I have come up with a vertical asymptote of -3, and I drew that in. The long run behavior, as I said, gets a little crazy because we end up with y equals 4x, which is not a vertical asymptote, but it is a line. And so we have an oblique asymptote. So I've kind of put that through here, all right? And then we have two x-intercepts, right? If we solve this equation, set it equal to 0 and solve for x, of course, you know, we could just jump to saying the numerator equals x. The numerator equals 0. And so we get x equal to 0 and x equal to -7/4. So I need to put my point in there, but we should have a point at each of these. There we go. All right. And then, of course, our y-intercept is also going to be at 0, because if your x-intercept is 0, that means your y-intercept is at 0 as well. Okay, so what's this graph looking like? Well, we have to conform to this vertical asymptote, go through this point. Looks like we have to kind of curl back around and go through this point and then conform to our oblique asymptote. All right, and so I know you might be thinking, well, wait, the oblique asymptote also goes through 0, 0. How can that work? But here's the deal. Functions are not allowed to cross vertical asymptotes because, of course, you're undefined there. But there is nothing wrong with having a function cross a horizontal or some other asymptote. All right, because you have to remember these asymptotes that are horizontal or oblique, remember they have to do with long run behavior. Okay, they're not about small values of x, they're about what happens for large values of x. So it's actually okay that we can cross that oblique asymptote. All right. At this point you might think, okay, now we've got our graph. But remember, you have to check on both sides of the vertical asymptotes, because there's values we can plug in over here. So the question is, you know, where are those values? We can either conform to this asymptote and then this one here, or we can come at it from the bottom and it can be down here. And that's where it gets a little sneaky. Well, if we plug in -4, all right, into our function, let's kind of see what happens. First of all, on the bottom, we'll have -4 plus 3, which is -1. Now on the top, we're going to have -4 here for where the x is, and then we'll have what? I think -16 plus 7 would be -9. So -9 times -4 is +36, but then that's divided by -1. So we'll actually end up with a -36. All right, and that's going to be sufficiently far down that it's actually going to be this piece down here. It's going to come up and conform to those two asymptotes. I should have had that a little bit more diagonal there. So it's going to come that way, conform, and go back down. The way we can tell this is we could figure out where these two lines intersect. All right. So we know that x has to be -3 at this point, and the other line, of course, is just 4x. So the y would just equal 4 times -3, which is equal to -12. So if that's at -12, then we know we've got to be down in this area here for our graph. All right. Well, that was a little tricky. Let's take a look at one more where we're given the formula, and then we'll close with one where we go the other direction. This last example is actually fairly straightforward until you get to the very end. There is a little twist when you get to the end, but go ahead. I think you shouldn't have too much trouble getting the basic information that you need. Just pause the video and then you can check your work with mine. Okay, see if this is what you got for your information. Alright, so I've put all the information in here. We've got two vertical asymptotes at 1 and 3. We have a horizontal asymptote also at 3, so you can see we've got that in there. And then, yeah, our x-intercept and our y-intercept are the same point, right at 0. So go ahead and see if you can sketch the graph, all right? Pause the video and do that. Okay, check and see if this is what you got. I decided just to draw in the parts that are between the two asymptotes and to the right, just to start here. I just plugged in positive 2 and got back, I believe, negative 12, right? Because we'll end up with negative 1 on the bottom and then 3 times 4 on the top. So get the negative here, so it's got to conform to the two asymptotes and hit that point. And then I just plugged in positive 4 and got back a positive number over here, so I knew it had to be, well, not just a positive number, but a number bigger than 3. So I knew it had to be up that way. Now, the part on the left, I wouldn't be surprised if you drew your curve, had it conform to this horizontal asymptote, come through this point, and then go on down. And if you did that, then you were probably doing what just about everybody does on this function. The thing is, if you actually graph this on the calculator, it doesn't look like that. It actually ends up looking like this. Conforms, comes down, and touches that point, and then it heads right back up like that. Surprises everyone. First of all, they can't believe that the graph would cross the horizontal asymptote, but remember I told you horizontal asymptotes only dictate what's going on for large values of x. It is okay to cross a horizontal asymptote. Not a vertical, but a horizontal. So why did it end up doing this? Well, first of all, let's check it out. Okay, if we plug in 1/2 up here, you're going to have a positive number up top. On the bottom, you're going to have a negative times a negative. So you see you'll actually have positive on the bottom too. So there's no way it can keep going down here. It's actually going to curl back and go up and conform to the vertical asymptote that way. What is another way you could know that it was just going to come off here, kiss the x-axis, and go back up? Have we seen that happen anywhere before? And yes, you're right. We have seen that happen when we dealt with polynomials that had double roots. And you see, that's what you have right here. You have, 0 equals 3 times x times x. Of course, the 3 can divide out, but you have two roots, two roots at 0. So this is what happens when you have a double root, right? It comes down and kisses the x-axis and goes back up. All right, one more example here. We're going to turn the tables and give you a graph and ask you to come up with the formula. Now this may seem like a daunting task because it's not the way we've been doing things, but this actually isn't all that bad. What you need to remember are a few key things, okay? When you're talking about vertical asymptotes, all right, vertical asymptote, you're looking at the denominator, right? Denominator. And when you're talking about, what's the numerator control, right? So vertical asymptotes, that's when the denominator equals 0, all right? What does the numerator control? What about when the numerator, equals 0? Yep, that's your x-intercepts, okay? So you can kind of set your factors using that information there, okay? And then once you have those factors set, then you can start worrying about things like the horizontal asymptote or the long run behavior, okay, what's going on there. And the last thing, if I were you, the last thing I would worry about would be the y-intercept, okay? Don't concern yourself with that till the very end. There might be some adjustment you can make, but hopefully the y-intercept will just work out for itself, all right? So pause the video and see if you can figure out what the formula is for this function here. Check and see if this is what you got. Okay, did you get this far? So, picking up on the fact that we just have one vertical asymptote at -3, we should have a factor of x plus 3 in our denominator. And then we do have two x-intercepts at -5 and -2, so we're going to have x plus 5 times x plus 2. All right. Now, the next thing to check on is the long-run behavior. All right, it looks like our graph is conforming to this horizontal asymptote of y equals -2. So you need to make sure that this long-run behavior will give you back -2. And this is probably the trickiest part of the whole problem. All right, so pause the video, see if you can figure out how to do it. Right now we don't have it. Right now our long-run behavior is x squared over x, which would just be y equals x, which is not a horizontal asymptote. So we need to make some adjustments so that our horizontal asymptote is y equals -2. All right, give that a try. All right, see if this is what you got. It's a little tricky, but this is what I got. All right, so for this long-run behavior to end up being linear, especially at -2, we had to get the degree on the top to equal the degree on the bottom. And I had x squared on top, so I needed to get an x squared on the bottom. So that's why I put the square here. I couldn't put another factor, like if you multiply by x, that introduces another vertical asymptote, and we couldn't do that, okay? So that's why we just square the bottom, all right? And then if we just put a little -2 over here, that'll put it at y equals -2, right? If we don't have the -2 there, then we just have x squared over x squared, which just gives us 1. So multiplying by the -2 puts it in the place we need it. All right. And last thing we need to check is our y-intercept. Is our y-intercept at -20/9? And I think we're in good shape. If we plug 0 in for x, we will have 10 times -2, which would be -20, and on the bottom we'll have 3 squared. So there we go. So worry about that y-intercept last. Don't let that be the thing that gets you. All right, set your factors in the denominator and the numerator first, and then the tricky part might be getting that long-run behavior to work out for you. Okay, you're going to see a good number of problems on the homework that are like this this problem here, where they give you the graph and they want you to come up with a formula.